All right, so this video is going to cover solving a differential equation involving a varying force. It really goes with our Unit 2 on dynamics, but it's got some more advanced calculus and algebra in it, and this is probably the only reason why I typically leave this for the end of the year. There's a lot to this. It's mostly mathematical. There's not a ton of physics involved with this. But essentially, we're looking at two types of varying force equations that are going to deal with resistive forces. So one, the object's going to start with some initial speed and slow down, and then the second one is going to start at rest and it approaches some terminal velocity. So you can see type 2 is like the coffee filter lab where we drop it down there. All right, so let's look at the first one. I think is the little bit more simple, where we just have one force acting on the object. So it's moving, and then you have some resistive force, minus kV, that is causing it to slow down. So notice I put the direction in there twice. Don't put a double negative in there. I have that negative sign to indicate that the force that's being applied is opposite the direction of motion. So I have both magnitude and direction in that force. So typically the first question, you can see from the notes, is you want to write a differential equation relating velocity, time, and the given constants. So step 1, Newton's second law. Step 2 is going to be replace your net force with what you know, what you're given, and you're going to replace your acceleration with your dv dt. This is a differential equation that could be solved later, but if they just want the differential equation, that's it. That's where you stop. Okay. Typically, the second part of the question, well, actually, just like a little bit of a side note, if we look at the value of the acceleration before it even begins to experience the resistive force, so if I just substitute in my initial velocity v naught, I know that this is the maximum value of my acceleration, and it's going to be decreasing as time goes on. So just keep that in mind, because we're going to be doing some graphs at the end of this. All right. Determine the velocity. This is now asking you to solve for the differential equation. So this is the differential equation that we started with. The first step is now going to be to separate the variables. Get the dv on one side and the dt on the other side, and you basically want to get all the constants with the dt. Do you have to do this? No, not really, but it makes the algebra a lot more simple when we get to the end and trying to simplify this expression. All right, so then we're going to integrate it. We're going to set up an indefinite integral here on both sides. So we got dv over v, and then we pop the constants out of there. And we should recognize this, and this is probably why I left it for the end. So you do the integrals. This is just a constant times t plus your constant of integration, and then 1 over v dv is going to be the natural log of v. So you have covered that in a calculus class. I'm not going to go over that. I can take these two constants together and combine them. You're going to see we're going to do this a lot. Add constants together and just call it another constant. And now I have something that looks like this, but I need to determine the velocity, not the natural log of the velocity. So I need to isolate v and solve for it. So how am I going to do that? I'm going to take the exponential of both sides. So take the exponential of both sides. So e to the natural log is going to give me just v. And then we should recognize that if I take e to all of this plus a constant, that is equivalent to just taking that constant and multiplying it times your exponential. So now we've got velocity as a function of time, but now we still need to get rid of this constant c. So we're going to use our initial conditions to solve for c. So at time t equals 0, we know that our velocity is going to be equal to the initial velocity. So I'm just going to plug in time t equals 0. It's equal to my initial velocity. This is all going to go equal to 1. So I know my initial velocity is my constant of integration. And now I've got an expression for the velocity as a function of time with all of it taken care of. So that takes care of that part. Big red box around it. So let's just highlight again the steps when you're dealing with a varying force, a force as a function of velocity. Write Newton's second law. Substitute for the net force on one side and replace the acceleration term with dv dt. Separate the variables. Put dt on one side, put dv on the other, put all the constants on the dt side. You constantly want to be organizing your algebra that way. Set up and solve. Get rid of your natural log by taking the exponential, and now you want to isolate v, and then your final step is to solve for c using your initial conditions. Okay, so again, mathematically, you could do some of these in a slightly different order, but I find, my experience, this is the most direct way to get to the final answer that they're looking for. All right, so continuing with that same question. So once you have a velocity function, you could be asked to find a position function or an acceleration function. It's just a matter of whether you're going to integrate it or take a derivative. So in this case, let's find the position function. So I just need to take the integral of my velocity function with respect to time. Again, I set up an indefinite integral here. Work through that. I'm not going to go through that part. You should be solid with that from your calculus class. Then once again, I'm going to solve for the constant of integration, knowing my initial boundary conditions. So at time t equals 0, I can substitute in what my initial position is going to be 0. So my constant is just going to be mv naught over k. So plug that in, and we could do a little bit of simplification there. And we have this exponentially increasing function that's going to approach this maximum value here. So what's the maximum value that it's going to approach? So we want to find x as t approaches infinity. Again, as t approaches infinity, we're just going to have this constant in front here. So again, as we're going to move towards creating these graphs, this is going to, our initial position is going to be 0, and it's going to increase exponentially to this maximum value, asymptotically to that maximum value. So let's look at these graphs again. We started with the velocity graph. So our velocity is v naught e to the minus kt. So that's going to start at some initial velocity v naught, and it's going to decrease asymptotically to 0 as it begins to slow down. Our x position is going to start at initial position 0, and again asymptotically approach this maximum value, which is mv naught over k. So we have that function that we solve for. And then finally, our acceleration function that I did in the very beginning, I said, well, what is that value of the acceleration initially, maximum value? So that just comes from the first slide, and that is going to decrease to 0. So we should be able to construct these graphs or maybe even pick them from a lineup. Again, the new AP test, who knows what they're going to put together. Maybe they're just going to say, pick the right shape, and you have to know what the shapes are going to look like. You know, they might not ask you to draw them, but they could say, you know, choose from the following, which one is the right looking one. So you should know what they look like. All right. The second type is the increasing speed. This goes back to the coffee filter lab, and we have an object that's being dropped. Again, it's got starts from rest, increasing velocity, and we know that as our object is decreasing, that velocity is going to increase. Our coffee filter lab had this as a function of v squared. That's a little harder to solve that differential equation, so it's probably more likely they'll give you a linear function of your drag as a function of the velocity. So again, we're going to follow the same steps, the differential equation. You're going to write Newton's second law, substitute the net force, and replace the acceleration with dv dt. So again, don't put the double negative in here. Don't tell me, oh, I know we've only just talked about the magnitude of these forces, but I'm putting that negative sign in again to just remind you that it's this resistive force. So mg minus kv, we still have the right idea that we're taking the difference between these two forces. All right, next step is we want to be able to determine the velocity of the object as a function of time. So this is the highlight of all the steps. Separate the variables. dv's and dt's on one side. Keep the constants on one side. Keep them away from the velocity side. Set up your integral. Do your get rid of your natural log that you're going to end up with. You're going to isolate the velocity, and then the last step is to solve for c using the initial conditions. This one is a little more challenging because it's got some more fancy calculus things that hopefully you guys are going to recognize. So separate the variables, which I have done. I need to set up an indefinite integral on both sides, but we can see this is a little more sloppy on the right side, so we're going to have to use a little u substitution. All right, so I'm going to let u equal mg minus k times v. And I'm going to take the derivative du to get that my dv, so I can do a substitution in there. So now I've got an expression where I can substitute dv to be minus du over k. I'm going to substitute that in for my indefinite integral here. I've separated my variables, substituted that in, but we got to take a step back. We want to keep this stuff all by itself. So always bring the constants over to the dt side. It just makes it a little bit easier in the end so that we just end up with that ln of u on the right side here. So I got minus k over m, indefinite integral over dt. All right, so carrying that over again, so this is simple on this side. I've kind of skipped a step. You're going to have a constant of integration on that side, but I've kind of already comboed it over here, ln of u, and then I've kind of worked my u substitution backwards and replaced it with the mg minus kv. All right, next step, get rid of the natural log by taking the exponential of both sides. So hopefully I've skipped a couple of steps here, but I think you guys should be comfortable with this algebra. So I'm going to have my constant in front now, e to the minus kmt. Again, I have my exponentially decreasing function. I get my mg minus kv. And now next step is we're going to isolate v. So in order to do that, I'm going to divide both sides by k. So I divided my m and brought my mg over. Left my v on that side, kind of done a couple of steps of algebra, but now you may be saying, well, what happened to this c? If I divide by k on this side, shouldn't there be a c divided by k? Well, c divided by k is just another constant. I'm just going to keep calling it c. So before we added c plus c and just called it c. Now I'm taking c divided by some constant k, and I'm just calling it some other constant c. Again, it all helps when we're kind of putting all the algebra together and keeping those constants all together. All right, so we're going to solve for c. What is it now? Using our initial conditions. So we have our velocity function. So at time t equals 0, our velocity is going to be equal to 0, so that this part of the expression is going to go to 1. So I get that my constant here is just going to be mg over k, and then I'm finally end up with that the velocity is mg over k times this exponentially increasing function. All right, so again, we should be able to graph those functions. I'm not going to go through the graphing again. But again, once you have your velocity function, you could either be asked to find a position function or an acceleration function. So for the first example, we did position. So for this example, we'll do the acceleration. And I'll do it all in one step here. Again, I'm hopeful that you are comfortable with doing this type of calculus now. This is really just a math problem. Step 1 is stating that my acceleration is going to be the derivative of the velocity function, and I'm going to take the derivative of what I solve for here. You're going to have to do a little product rule going on there, some simplification, and you just end up with the acceleration due to gravity, e to the minus km over t. So again, your acceleration is going to exponentially decrease from its maximum value of g when it's in free fall, decreasing to 0 as t goes to infinity. So you should be able to do all of these graphs for the two different types. One where your velocity is going to be increasing, type 2, like a terminal velocity type problem, or second type where the velocity is decreasing. So you have maybe a box that's being pushed along a horizontal surface and slows down. So these types of problems have been on the AP exam many times. So it's definitely how they could write this to make it suitable for an online assessment. Not really sure, but you should be familiar with how to do the calculus. If you can just set up the physics, I wouldn't worry too much about finishing the calculus part of it. I think it's more about knowing what the shape should look like, even if you can't get there with all the algebra and the calculus. But at least knowing how to set up the differential equation. And maybe you can't get through the whole solution, but you can get part of the way through. And it's all about the partial credit. All right, good luck. I know that was a long video, but that's the end of the year. Congratulations.